right, let's take a look at problem 2 from chapter 9. So we're told the molar enthalpy of a binary liquid system of species 1 and 2 at fixed temperature and pressure is represented by the equation given below, where H is in joules per mole. Determine expressions for H bar 1 and H bar 2 as a function of x1. Numerical values for the pure species enthalpy H1 and H2, and numerical values for the partial molar enthalpies at infinite dilution. Great, right? So a lot of things that they want here. And so what I have pasted here is I'm going to assume that you watched the screencast that I just recorded on calculating or simplified equations for calculating partial molar properties in a binary mixture. And so I won't go off on motivating where these came from and why it's advantageous to use these. All right, for that, see the last screencast. All right, so the first thing I'm going to do is I'm going to take an aside, right? And so I'm going to take an aside, and you can ignore all of this for the case of problem solving. But what I want to just mention is the expression that's given here is a very common expression used for correlating or analytically modeling molar properties in a binary mixture, right? And it's going to take the general form, and I'll write it in terms of H, of my molar property of interest is equal to x1 times h1 plus x2 times h2 plus x1, x2 times delta H of mixing, right? And we'll talk more about this. We haven't discussed property changes upon mixing or anything else yet in chapter 9, so we'll revisit this, but I just want to kind of put it out there, okay? Because you're going to see expressions like this a lot, right? This is kind of the conventional way of correlating properties of a binary mixture. Is done as such, right? And so what happens is we have x1 h1 plus x2 h2 plus x1 times x2 delta H of mixing. So this term on the right, so this is my property change upon mixing, and it's x1 times x2 times delta H of mixing, reason being, in the limit that I have pure component 1, well then x2 is equal to 0, and this term 0. And the limit that I have pure component 2, well x1 is equal to 0, this term gets killed. So in both of my pure component limits, this term is killed. Okay. Then looking at this, in the limit that I have pure component 1, x1 goes to 1, x2 goes to 0. So in the pure component limit, right, I have the correct limiting behavior, the H is equal to H1. In the limit of pure component 2, I have the correct limiting behavior that H is equal to H2. Okay. And now, this, right, is going to essentially be H ideal, right? And so when I have a composition other than my two pure component limits, well then my enthalpy is equal to my I'll call it my ideal enthalpy here, okay, plus then I've got my property change upon mixing over here. Okay, cool. All right, so I've got the value of an ideal solution plus my property change upon mixing. All right, this functional form is such that my parameters, the parameters have physical significance, right? So h1's 400, h2, right, is 600, and then 40x1 plus 20x2, well, that's just an analytic equation that was used to fit, right, or model delta H of mixing. Okay, so we'll come back to this later. I just wanted to mention it as an aside because you'll see expressions like this a lot, where it's first parameter times x1, second parameter times x2, then it's x1 times x2 times some function of composition, right, that's used to model my property change upon mixing, right? And for an ideal system, it might even be just a constant. And then, this would be some, function that if it's Excel, I could keep increasing the number of terms in my polynomial until I'm satisfied with how I fit the data. Okay. All right, but that's my aside. We're going to come back to this problem. Okay. So we're asked to get expressions for h bar 1 and h bar 2, and then expressions for pure h1 and pure h2. Okay. All right. So let me get h1 and h2 first, just because it's here. Okay. And so the idea is, we already kind of mentioned it, is I know that my enthalpy, right, is a function of, it's going to be a function of temperature, pressure. We're not explicitly given temperature and pressure, but then composition, right, x1. Right? I don't need to list x2 because x2 is 1 minus x1. Okay. Well, H, okay, is going to correspond to the enthalpy of my mixture from pure component 1 to pure component 2. So how I get h1 and h2 is, well, h1, right, well, that's going to be the limit as x1 goes to 1, right? And if x1's going to 1, that's the same as x2 is going to 0 of h. So if I look at my equation for h, okay, and the limit that x1 goes to 1, right, this is 400, this is 0, right, this is 0. Okay, so what I'm left with is just this first term, right, which is 400, right? And it would be joules per mole since that's my units that we're given, right? But it's going to be 400, okay, joules per mole. In terms of getting H2, okay, again, I'm just going to look at the limit. H is going to correspond to my molar enthalpy from covering all the way from pure component 1 to pure component 2. Okay, so H2 is just going to be the limit. Okay, so I'm looking as H2 goes to 1, which is equivalent to X1 goes to 0 of H. So if X1 goes to 0, that's 0, right? This term's 0, and I'm just left with 600. Okay, so H2 is just going to be 600 joules per mole. Okay, cool. Now let's get our partial molar properties. Okay, and so this is where I'm going to use my simplified equations that we worked up in our last screencast. Okay, well, and before I even do that, okay, the key is in both of these I need derivatives with respect to x1. I can make that a derivative with respect to x2 since dx2 is just negative dx1. Okay, but we'll stick with x1. And so what I'm going to have to do with this equation is I'm going to have to get rid of x2. So I'm going to have to go through and replace x2 with 1 minus x1. So I'm going to substitute in for x2, 1 minus x1, and then I'm going to attempt to expand and simplify and wish me luck. Okay. And now, actually, this would be nice. We could do this in Matlab with the symbolic calculator. Actually, maybe we should do that. But let me express it out by hand, right? And then we could always do it in Matlab using symbolic calculations. All right. So h is equal to, now I'm going to punt a little bit, and I'm just going to call this A, B, C, and D, right? Just so that I can expand and then eventually simplify. Okay. So I'm going to have A x1 plus B x2 plus x1 times x2 times cx1 plus dx2. Okay. Just trying to make the term simple for me. Okay. All right, so first let me expand this term out, then I'm going to replace x2 with 1 minus x1. So I have h is equal to ax1 plus, okay, and I'll get the x2 in there, plus bx2 plus c times x1 squared times x2 plus d x2 squared times x1. Now I'm going to plug in x2 is 1 minus x1, so h is equal to ax1 plus b times 1 minus x1 plus c times x1 squared times 1 minus x1 plus d times 1 minus, I'm going to write this one on another line, plus d times 1 minus x1, okay, and I'm going to write it, just, it's x2 squared, so instead of 1 minus x1 squared, I'm going to do 1 minus x1 times 1 minus x1 times x1, okay, and so we're just going to expand again. So then h is equal to ax1 plus b minus bx1 plus cx1 squared minus cx1 cubed plus, okay, on the next line, oh boy, help me here. So we're going to do one term at a time, so this could be d times, I'm going to do 1 minus x1 times 1 minus x1. So actually I'm going to write this as dx1, and I'm going to expand that inside first, dx1 times, so it'll be 1 minus x1 minus x1 plus x1 squared. Okay, so h is, and actually let me just play with this term and then we'll plug it all together so I'm not just rewriting everything down. So this term then is dx1, so this is minus x1 minus, so minus 2x1, so this could be minus 2 minus 2d x1 squared, and then plus dx1 cubed. Alright, so now with that, I'm going to try and collect terms in terms of power of x1. So then h is going to be equal to, so first we'll do, let's go big to small. So we'll start with x1 cubed. Okay, so in terms of x1 cubed, it will be, so this, well, let's go left to right. So x1 cubed, I'm going to have a minus c plus d. Okay, let's do x1 squared. So x1 squared, I have another minus c, and then minus 2d. Okay. Power 1, so plus x1. So now I have an a, I called that a1, a minus b plus d. And then my order x to the 0 is I just have constant b, right? Just b. Phew. Alright, so now if I go to my first equation, so in x2 here I'll replace with x1. So f bar 1, okay, so f bar 1, so h bar 1 is equal to h minus, or plus, okay, x2, which is 1 minus x1 dh over dx1. Okay, and then I'm actually going to need dh dx1 for the second term as well. So let's just get that first. Okay, so now that I have this equation up here, right, dh dx1. Okay, well, that's just a constant. Okay, so it's going to be so negative c plus d. Okay, my constant, and then power rule. So it's going to be 3 times that constant, x1 squared, plus my constant, I'll first write my constant, minus c minus 2d. Well, then the derivative of x1 squared is going to be 2 times x1, okay, plus. Now I'm on the third term. It's just going to be my constant because the derivative of x1 is just 1. All right, and then that final term, derivative of b, is just going to be 0. Okay. All right, so I've got dh dx1. So h bar 1 then is going to be equal to h plus 1 minus x1 times dh dx1. Yeah, so my apologies. I probably should have done this in Matlab, the symbolic calculator. Maybe we'll have another video in which we do that. Okay. But, all right. I could do limits in Matlab too, but let me get this. All right, so now I have h bar, my expression for h bar 1. So then h bar 1 is going to be equal to, my expression for h was up here. Okay, so let me write that all up. And then it's going to be plus 1 minus x1 dh dx1, which is this guy, and then I will collect terms. I'm not going to simplify from there because that'll take me too long. So x1 cubed minus c plus d plus x1 squared minus c minus 2d, okay, plus x1 a minus b plus d plus b plus 1 minus x1 times that equation I just worked out, which is this. So still within the brackets. Okay, so that'd be my expression for h bar 1. I could expand and simplify, but I don't know. I don't know if it's worth it at this point, right? It's going to take me more time to write out that work. And then you do something similar for h bar 2. Just h bar 2 is h minus x1 dh dx1. Okay, boom. And so I could work out my expression for component 2 as well, and then simplify and take it from there. Okay, so and then once I have this in terms of x1, if I wanted to get it in a form similar to I had up here, right, I could replace occurrences of 1 minus x1 with x2, and life would be okay. Right, just like even here, I could just put in x2 and call it a day. Okay, but I'm going to leave it like that for now. Okay, and then we're asked for h bar 1 at infinite solution. Well, that's just going to correspond to the limit as x1 goes to 0 of h bar 1. Okay, so the infinite solution limit, we'll talk about this more later on. Okay, this is going to correspond to maximum deviations from ideality. This is a single molecule of component 1 in a system of component 2. So it's going to be as uncomfortable as component 1 could possibly be. And so if I were to look at this equation, and if I were to plug in x1 equals 0, well, this first term 0, that's 0, that's 0, okay, b would live, okay, plus b, okay, and then I would have, this is just 1, but if I look in here, all right, that's 0, that's 0, okay, and then this would live, right, so it'd be 1 times, this would be the only term left, so it'd be plus b plus a minus b plus d. Okay, so my b's would cancel, and I'd be left with h bar 1 at infinite solution is equal to a plus d. All right, and if I had worked out an expression for h bar 2, I could do exactly the same thing. All right, so again, I could simplify my expression for h bar 1. I'm not going to do so here in the interest of time. All right, I could work out an expression for h bar 2, all right, and then simplify and get h bar 1 in solution, but I'm not going to do so here in the interest of time. What I'm going to do is I'm going to stop this screencast, and then I'm going to pop up Matlab, and I am going to symbolically solve this one in Matlab. Okay? All right, I will see you over there. All right, so I have my solution here that we just discussed and worked out by hand. So I have it saved here as a PDF, and so I'm just going to go over to Matlab and try and solve the problem using Matlab. Okay, cool. And so what I'm going to do, okay, so I have this script, problem 2, fall 2023. And I'm just going to define some symbolic variables, and so my symbolic variables are going to be x1 and x2. Okay. All right, so now what I'm going to do is I'm going to define my enthalpy function. Okay, and so h is equal to 400 x1 plus 600 times x2, okay, plus x1 times x2 times, I've got to get the numbers, 40 x1 plus 20 x2. Okay. I don't know why it's getting F in here. I don't. Okay. Cool. All right, and so it's going to keep running it. All right, so I can check to make sure I have things right. Okay, so now I have my expression for h. Okay, now first thing I'm going to do is in my expression for h, I'm going to substitute in that x2 is equal to 1 minus x1. Okay, so h, so I'm going to hu for h update is equal to, so I'm going to subs into my expression for h, and I want to place x2 with 1 minus x1. Okay, so now I should have hu, right? And hu, okay, is just h. Okay, and all I've done is I've substituted it into my original expression for h, 4x2, 1 minus x1. Okay, all right, cool. And actually, let me do something. Let me call that h, and we can call this h as well, right? I can just overwrite what I had before, and life is good. Okay, so it's not ideal since I'm just overwriting my previous expression, but so be it. Okay. All right, so now I have my expression for h, and now I want my expression for h bar 1. H bar 1. Okay, well then how do I get h bar 1? Well, and actually let me take it in first steps. Let me do dh dx1. So in both my expressions, I did an expression for the derivative of h with respect to x1. So that's going to be diff. My expression is h, and I want to differentiate with respect to x1. Okay, cool. So let me clear all. So now if I run this, now I have my expression for h, and now I have my expression for the differential of h with respect to x1. So h bar 1 then is just going to be equal to, well, I've got to pull up my expression. So h bar 1 is going to be h plus 1 minus x1, or x2 times df dx1. Whew. So h bar 1 is going to be equal to h plus 1 minus x1 times dh dx1. So I got an error. H bar 1 dh. Oh, I need dx1, right? That's not defined. Okay. So h bar 1 is equal to that. All right. Cool. Okay. If I wanted my expression for h bar 2 is going to be equal to h minus x1 times dh dx1. And so just like that, I have my expression for h bar 1 and h bar 2. All right. If I wanted to try and simplify, I could. Right. Pretty sure there's a simplify function. Let me do, well, I'm going to try. So it's going to be simplify, I believe. Well, and I've got to try and recall my, because there's an expand and then there's a simplify. So, nope, it's not simplify. I might need to come back to this one. Okay, but regardless, let's see now if I can get my limit. So h bar 1 inf, okay, is going to be the limit. Okay, so I've got a limit function. My function is h bar 1, okay, and it's going to be comma, and then I think it should just be able to type in 0 because it's only a function of x1. Okay, let's see. So h bar 1 at infinite dilution is 420. Okay, and what did we have? H bar 1 is a plus b. Okay, a plus d, right? A plus d, right? 400 plus 20, 420, right? Cool. So I got h bar 1 at infinite dilution. If I want h bar 2 at infinite dilution, it's going to be limit h bar 2, and then it's going to be limit though. So I only have things in terms of x1. So now I'm looking at the limit that x1 goes to 1. Okay, so if I run that, h bar 2, 640. If I want to get h1, always said h1 is the limit that, so the limit of, so I'm looking at the limit of x1 goes to 1 of h. Just like if I wanted h2, that's the limit of h as x1 goes to 0, because as x1 goes to 0, x2 goes to 1. Alright, so h1 is 400, h2 is 600, which matches perfectly with our initial discussion. Alright, so cool, right? So I could do this all symbolically in Matlab. I'm pretty sure, see, this is where I'm just a little rusty on symbolic calculations. I haven't done them for a while, but I'm pretty sure that there's a simplify function. So actually, let's just try it now that we have this all working correctly. And so I want to try h bar 1. Oh, let me mention the other, so besides limit, the other thing you could do is subs. Okay, so if I wanted to do subs, I could take my expression for h and I could substitute in a value of x1 of 0, of x1 of 1. Alright, so if I do this, alright, h1 check, so subs is going to take my expression here, right, for h, and it's going to replace x1 with the value of 1. Alright, just like we did up here, where we replaced x1 with x2. Okay, so I'm going to comment that out. Okay, but alright, so let's see if we can simplify. I'm pretty sure there's a simplify. So I'm going to try h bar, just do like h, this is going to be, let's playing with h. Because right now what I have for h, let's see, h is this. So I want to try and play around with h in terms of seeing if I can expand and simplify. Okay, so I'll call this h. I don't know, I don't want to call h underscore 1 as I try and iterate. So I'm pretty sure I can expand h with respect to x1. No, it doesn't like that. Yeah, so this is where there's separate symbolic functions for expand. So I guess it's just expand h. Okay, so h1, so this is what happens when I expand h. All right, 20 x1 cubed minus 180 x1 plus 600. Okay, so did we simplify? Yeah, so I'd have to plug in my terms. Right, so I have minus 20 x1 cubed. So what is d minus c? D minus c would be negative 20. Okay, so my x1 squared term goes away, right? Negative 2d minus c. Okay, so it seems like maybe I have an error in my calculation, because minus c minus 2d, is that equal to 0? Minus c would be minus 40. Minus 2d would also be minus 40, but the sign of one of these is that means it's off, right? Because when I collected terms in x squared, right, where could I have messed up the sign? That's minus 2d I had here. The other one comes up from the c. Yeah, because this is plus cx squared minus c x1 cubed. Yeah, so this should be a plus c x1 squared. So this should be a plus c minus 2d, right? Hey, we just found a typo. That should be a plus c. All right, my sign was messed up. Okay, cool, right? So I could expand, okay, and I could do the same thing. So h bar 1, okay, okay, and so I'm just going to comment out some of these so I don't have as much being printed to screen. Okay. Okay. So if I run this, so there's my expanded h. Hey, here's my simplified expressions for h bar 1 and h bar 2. Right, so h bar 1 is just 40x1 cubed minus 60x1 squared plus 420. And then there's h bar 2, right? So I don't even need to simplify. So using Matlab, all right, I just found out that I, uncovered that I had a, I guess, typo here, that when I expanded, this should be cx1 squared minus cx1 cubed. This should be a plus sign here, right? So that this term is 0, right? And I just discovered it because, well, Matlab doesn't struggle with algebra at all. And so here's my simplified equation for h bar 1 and h bar 2. All right, and then in terms of getting my other quantities of interest, right, I could just use limits to get h1, h2, then even those limiting values. Okay, and then h bar 1 at infinite dilution, right, x1 is just 0, 420. H bar 2, right, well, this would just be x1 goes to 1, so 40 plus 600, right, hold on, it should be 600 plus 40, right? Oh, why am I going to... H bar 2 in the infinite dilution limit, oh, should be 600 plus 40. Oh, yeah, 640. I'm sorry, I was looking at the wrong term, right? So everything works out. So cool, right? I could have done this in Matlab too and saved myself a whole bunch of aggravation. Okay, cool. Hope that helps. We'll see you in class.